So I'm Ryan Doyle, and I've been working with Dr. Jeffay, Dr. ICAT, and Jacob Massey, who's another undergrad, on testing the effectiveness of AQMs at improving network performance. And before I get into exactly what that means, I'll go into a bit of background on how the internet works. So information on the internet is sent in the form of packets, and you can think of a packet as analogous to an envelope that you would put in the mail. You put what you want to send in, so there's a data component, but there's also a bunch of header information that's used for routing, such as the address and return address you'd write on an envelope. In this sample network to the right, if machine A wants to send information to machine B, the object or whatever it's trying to send will be split up into packets and then sent to the router that machine A is connected to. That router, for each packet, makes the decision of where to forward it to the next hop or the next router in the network. And each router makes a decision about where to forward the packet until it finally arrives at its destination, in this case, machine B. The internet, however, makes absolutely no guarantees. You're not guaranteed that data will arrive uncorrupted. You're not guaranteed that it will arrive in the same order it was sent. And you're not guaranteed that it will arrive at all. So that's where the Transmission Control Protocol, or TCP, comes in. TCP provides these guarantees, and it also provides what's known as congestion control. So if a lot of people are sharing a link, it's possible that they're trying to send more data than the link can support at any given time. So TCP attempts to detect this and slow down the rate at which it's sending information to ease the congestion and ease up the bottleneck. This is a graph of how TCP's congestion window changes over time for two different versions of TCP. The congestion window is just one of several variables that are taken into account in determining how much data TCP can send in a unit of time. So at the start of a connection, TCP exponentially increases the rate at which it's sending data until it reaches a threshold, and it increases linearly until it experiences a drop. And I'll define that in just a second. But the key thing to know is regardless of TCP version, once a dropped packet is experienced, it cuts the throughput, or the rate at which it's sending data, tremendously, at least in half. So let's go back to routers for a second. Each router has a series of queues in it, one for each network interface. And if the queue is empty, that means that traffic is entering the router at a slower rate than the router is capable of processing it. So there's no congestion. All the traffic that arrives flows through quickly. But what happens if data or packets begin to arrive at a faster rate than the router can process them? In this case, a queue begins to build up, represented by the blue. And even if the rate at which packets are arriving at the router decreases to match the router's ability to send them back out, you'll have what's now a standing queue. And queues are processed in a strict FIFO order, so every packet arriving at the router has to wait for every packet that arrived before it to be processed before it's processed. So this standing queue adds a certain amount of delay to every single packet that's trying to be sent through that router. What happens if the rate at which packets arrive stays too high for too long? Well, the router runs out of memory to store the packets in, the queue becomes full, and every packet is dropped. It's literally gone. And it's up to TCP to recognize that this has happened, to retransmit the data, but also to perform the congestion control I described earlier and limit the rate at which it's sending data in an attempt to give this queue time to shrink in size. But in doing so, if a lot of connections lose packets at the same time, then a lot of connections will dramatically cut the rate at which they're sending data, which can actually overcompensate for the congestion and result in an underutilization of the link itself. So if you wanted to have the highest utilization of the link possible, you would, in theory, want an infinite queue. But if you have an infinite queue, it allows for an infinite amount of delay to build up over time. So the real problem here is, how do you balance limiting the amount of delay in a queue with not cutting the throughput more than you have to? And this is something that computer scientists have been studying for decades, and it's the problem that AQMs try to solve, or active queue management algorithms. So AQMs run on routers, and they replace this default FIFO or drop tail method of queuing with the goals of reducing latency caused by that buffer bloat or the standing queue, and improve link utilization and throughput. They do this by monitoring the queue and then dropping packets selectively before the queue becomes full. So the idea is that if you drop a select number of packets and cause a select number of TCP connections to reduce the rate at which they're sending traffic, overall, you'll maintain a higher link utilization while still managing the buffer. As an alternative to dropping packets, active queue management algorithms can also use ECN, which is explicit congestion notification, where a packet that would have been dropped has a bit in its header set, so the TCP connection reduces the rate at which it's sending data as if the packet had been dropped, but it doesn't have to resend that particular packet. So in theory, ECN would provide better performance. As an example of how these algorithms work, I'll talk about Codel, which is a newer AQM and one of the ones we're studying. Older AQMs often use the number of packets in the queue or the number of bytes in the queue to measure queue length. But where Codel really stands out is it actually measures the amount of time a packet was delayed by waiting in the queue. So it's actively measuring one of the two characteristics it's trying to balance. Codel works by timestamping every packet as it arrives at the router, and then as the packet is being processed, Codel checks the timestamp and determines its sojourn time, or how long it was in the queue. It keeps track of the minimum sojourn time over certain intervals of time, and when that minimum has exceeded a target value for at least a particular interval of time, it enters its dropping state. And upon doing so, it immediately drops one packet and then sets the time for the next drop. As more drops occur, the amount of time between them decreases in inverse proportion to the square root of the number of drops that have occurred since the dropping state was entered. And the reason for this is that it has been shown that this causes a linear decrease in the amount of packets arriving at the router. So it's much more controlled than the global synchronization you get from drop tail queuing once the queue becomes full. And then after a sojourn time is seen that's under the target value, Codel exits the dropping state and continues processing as normal. So what are the specific goals for our research? We're studying 3 different AQMs: Codel, a variant known as fair queuing Codel, and PI-E. And we're analyzing response times and average throughput in a real-world setting, or a laboratory that emulates a real-world setting, in an attempt to compare how well these algorithms perform against each other and against the default FIFO queuing. We want to test how well these algorithms perform at varying levels of link utilization and thus varying levels of congestion. So we want to test 80, 90, and 98% link utilization. We also want to study how well these AQMs perform in ECN mode versus drop mode. So how do we do it? Well, there are a series of software tools that we use to help us. We don't want to run software simulators that simulate network traffic. We want to know how well these AQMs perform in real-world settings with real-world data. So we use capture tools like TCP dump or various DAG tools to actually capture traffic from UNC's main link to the rest of the internet. We then convert this traffic into a format we call CVEX, or connection vectors, and use a program developed here called tmix to replay these same connections between pairs of machines. So we don't have to worry about patterns in our traffic. We're actually replaying real traffic. As tmix runs, it collects data on various metrics, including the response times we're interested in. We use the same capturing tools to monitor our experiments and a program we call BPFMon to analyze the average throughput to get our final metric. This is a diagram of our network. It's completely isolated from the rest of the campus's internet, and none of the machines beyond the one in the middle at the bottom actually has an internet connection. But we have 4 pairs of machines that all run tmix, with one machine on the left and one machine on the right. The machines on the right simulate UNC. All the traffic that was leaving UNC is sent from right to left. All the traffic that was sent and received at UNC goes from left to right in our network. And these 4 machines on either side are connected to switchers, which are then connected to routers. And the link between the 2 routers is emulating that link between UNC and the rest of the internet. By nature of the captured traffic we're replaying, much more data in our experiments flows from left to right than right to left. So we want our AQM to run on the most congested area of the network, so we put it on the left router just as it's sending information out onto that main link. And we have a tap and a monitor machine that allows us to capture a copy of all of the traffic during our experiments that we then analyze after the fact. But we have to calibrate this network. Since we only want to know how AQMs perform under congestion that we're controlling, we want to make sure that nothing in our network is impeding or altering the flow of packets in a manner we aren't anticipating. So the theory is, as we increase the number of connection vectors that any pair of machines are sending or replaying, there should be an approximately linear increase in the amount of throughput seen on our main link. So we ran a collection of experiments here, and these graphs have the number of CVECs on the x-axis and the throughput in megabits per second on the y. And the y-axes are scaled differently just because more traffic, as I said, flows from left to right than right to left. Each of these blue dots represents a 1-hour experiment replaying up to several million connections and up to hundreds of millions of packets between one pair of machines. And we can see that the trend becomes nonlinear at that second to the rightmost point. So we know that each pair of machines can safely replay approximately 1.68 million connections and generate approximately 160 megabits of traffic. And we'll do that on all 4 of our pairs of machines. So what are we doing next? Well, I'm a BSMS student, and we're continuing this project next year as my master's thesis. And as you may have noted, 160 megabits per second times 4 won't do much to congest the links that we're using. It's a 10 gigabit per second link between the 2 routers. So we're currently investigating different methods of creating the congestion at the point in our network on that left router that we're interested in, so that we can test under the 80, 90, and 98% link utilization. We also need to acquire a more recent trace. The data we're replaying was captured in 2008, and we aren't really interested in how well Codel would have worked or Pi would have worked in 2008. We want to know how well it would work now with 2015 traffic patterns. So we're going to acquire a new trace and use that for experiments. And finally, we'll be in a position to run our experiments with Codel, fair queuing Codel, Pi-E, and FIFO as a baseline, using response times and average throughput as our means for comparison. Thank you.
Questions?
So what slowed you down? Why couldn't you finish this audit as part of your bachelor's thing?
So there's a lot that goes into setting up a network around here. A big part of it was acquiring the machines. And then we had to work on setting each of them up, setting up the routing. We actually had several hardware failures along the way. We had to replace components. And we discovered, I guess late last semester, early this semester, that we actually needed to use modified kernels on the routers. So working through all of that, and then we did 12 or so calibration experiments that are an hour long each, but take at least an additional hour to process. So there's just a lot of time that goes into even getting this far.
You said that using this recorded, in quotation marks, real world data, you avoid patterns. Of course you don't avoid patterns, you just have patterns you didn't control for.
If I said that, I didn't mean to.
Okay.
I meant to say that the patterns visible in traffic will change as our use of the network changes. So in 2008, we might have been streaming less YouTube videos or something like that. So I meant to just say that instead of having to worry about what patterns to replay in a simulator, we naturally have any patterns that are mimicking the real world by nature of using the real world traffic.
Can I ask a question? What is your hypothesis on what results you'll get with the different methods?
So similar research was done in about 2007 or so, and it found that earlier AQMs showed some promise when they were using ECN, but the benefits weren't that dramatic over drop-tail queuing. So I would like for Codel and PyE to perform well, because that gives me a more exciting paper. But we'll just have to see, because the relationships between TCP and the queues at the routers and the AQMs are very complicated and hard to predict.
Other questions?
I'm slightly confused. What's your metric of performing well?
So performing well is basically performing at least substantially better than drop-tail queuing, what's currently used today, the unmanaged queues at the routers. So response time is basically by the time you send a packet from one side of your network out into the internet and it's received at a server, how long does it take for you to get a response back? So in measuring that and seeing if the AQMs decrease response time, we see if your latency in your video game will be lower with this AQM or real world impacts like that.
Do you expect the different applications that people are using to have different effects based on which kind of router you're using? Whether people are loading web-based traffic or playing YouTube or something like that?
So different patterns of traffic do respond differently to these AQMs, and that is part of the reason why we wanted to use a real trace instead of attempting to simulate everything. So we're kind of accounting for that just by using the real trace, and we're generating cumulative numbers for just your typical internet traffic without worrying about breaking it down by type.